with Geometry Lesson 6.1, and we will be talking today about classifying polygons. Now, what we need to think of is we have two-dimensional shapes, and when we look at two-dimensional shapes, what we're going to do this chapter is we're going to work on breaking those two-dimensional shapes down and classifying them, much like we did triangles last chapter. Well, when we looked at triangles, we took those triangles and we classified it as, by sides, which would be scalene, isosceles, and equilateral. And then we did it by angles as well, by right, acute, obtuse. And we classify those triangles into two different types of classifications, and which really is just looking at more and more specific types of triangles. Well, we're going to do that with all our shapes in general this chapter and into chapter 8. So we need to classify polygons. First off, we need to look at what is the definition of polygon. So I'm going to give you my generic definition. A polygon is a two-dimensional shape. Two-dimensional shape that is closed, meaning each side meets another side. There's no openings. That is closed with no curves. Okay, so that's my generic Mr. Dreher definition of what a polygon is. It's a two-dimensional shape that is closed, meaning each side meets another side with no curves, meaning if you think of this, you start thinking a circle. Is a circle a polygon? No, a circle is not a polygon because it is curved. A polygon is made up of segments, and segments cannot be curved. That's why a circle would not be considered a polygon. So if you need to, you can pause to finish writing that down. Now we'll move on. So what we're going to look at today is we have all our two-dimensional shapes. Now what we can do is we can break those two-dimensional shapes down into polygons. And the other side would be anything that is a non-polygon. You start thinking of non-polygons. It's anything that doesn't come and close itself, or anything that has a curve. So your circles and your ellipses are non-polygons. And then polygons would be everything from your triangles to your four-sided, your five-sided, your six-sided shapes that have no curves and are closed. So we could get more and more specific with the types of polygons we had. We went from polygons and we looked at triangles last class, which is a specific type of polygon, which then we went even further and classified that by sides. Today we're going to look at four-sided shapes, which some of you may know as a quadrilateral, and this whole chapter is spent on looking at what are more specific types of quadrilaterals. That's what we're going to look at this chapter. Right? So we're looking at types of polygons. Right, so when we want to go at what types of polygons we have here, we first look at the number of sides. Okay, so if we look at the number of sides here, we have 1, 2, 3 sides. Well, we should know, what do we call a three-sided polygon? We call a three-sided polygon a triangle. Okay, let's move on to the next one. We have 1, 2, 3, 4 sides. What do we call a four-sided polygon? Now some of you may be thinking square, rectangle. Well, those are all types of four-sided polygons, but every four-sided polygon in general is called a quadrilateral. Okay, quadrilateral. The prefix quad simply means four. You have your quadriceps, the muscles in your legs. The reason they called that a quadriceps is because there's four main muscles that make up the quadriceps. Right. Now if we look at this, 1, 2, 3, 4, 5, now we have 5 sides. That is called a pentagon. Anytime you hear the word penta, that means 5. When you hear a pentathlon means you're competing in 5 track events. 1, 2, 3, 4, 5, 6 sides is a hexagon. We go 7 sides is a heptagon. This is probably the most confusing. Heptagon. 8 sides, that one's kind of obvious there. A lot of people know that as an octagon. It's your stop sign. When we have 9 sides, we actually have two names. We can call it a nonagon, which is probably the one we're going to use. Some mathematicians also call it an enneagon. Alright? The one we will probably use is I will most often call it a nonagon because it's like a ninagon. It makes sense to me. And then 10, this is the last one. The prefix for 10 is a decagon. Just like a decathlon, you do 10 events. A decagon has 10 sides. Deca means 10. Right? So there's our 8 that we're going to name. Now, anything after 10, they have names for them. They apparently have some boring mathematicians that come up with names for all these. Um, you know, but then you could go a 27-sided shape, and they have a name for it. It's just really long. But what we're going to do, anything after 10, so if we have 11-sided figure, we're just going to call it an 11 gone. 12-sided, 12 gone. If we have a 20-sided figure, we're just going to simply call that a 20 gone. So we're going to kind of cheat and make it a little bit easier on ourselves. For anything after 11, or anything after 10, we're just going to call it a 11 gone, 20 gone, 30 gone, 100 gone. Like I said, they actually have names for most of them. Some of them are just really, really long, and I don't want to deal with them. Okay, so there's our types of polygons. So now we have more specific types of polygons. And again, like our branches, you can see our tree. It's polygons, we went triangles, and we went more specific. Quadrilaterals, more specific. We could get into pentagons, hexagons, all that, and look at more and more specific types. Right? And now what we need to do is look at this part and tell whether the following, decide whether the following figure is a polygon. If so, tell what type. If not, we're going to explain why. Okay. So if we look at number one, is this a polygon? Now remember, we need it to be closed with no curves. That was kind of my definition of what a polygon is. So we need it closed with no curves. So if we look at this, is this a closed shape? Yes. Are there any curves here? No. So is this a polygon? Yes. All right, and then we need to get more specific. We need to say what kind of polygon. 1, 2, 3, 4, 5. It has 5 sides, so that guy is a pentagon. So yes, it is a polygon, but more specifically, it is a pentagon. All right, let's go to number 2. Is it closed? Yep. Every side meets another side. Is it curved? Nope. So is this a polygon? Yep. So this is a yes. Now, more specifically, 1, 2, 3, 4, 5. We have 6 sides, so we would call this guy a hexagon. Now, again, we have two different types of shape. This guy doesn't have any indentations, but this guy's got this little indentation here. Now, that's something we'll talk about in Chapter 8, as this being convex and this guy being concave. Now, if we look at number 3, is this guy a polygon? Is it closed? Well, no, there's a little opening right here, so I could kind of sneak in right there if I wanted to. So is this a polygon? No. Now, to explain why not, I'm going to say it's not closed. Again, that's kind of a Mr. Dreher generic definition that is closed with no curves. So we look. All right, if we look at 4, is that a polygon? Is it closed? Well, yeah, it's closed. Are there any curves? Yes, there's a curve. So is this a polygon? No. Explanation simple. It's curved. Right? Let's go to number 5. Number 5, is it closed? Yeah, there's no openings around here. No little mice can get in there or anything. Are there any curves? No, there's no curves. So is this a polygon? You betcha. Now let's count. 1, 2, 3, 4, 5, 6, 7, 8. So that would be called 8 sides is an octagon. Right? So number 6. Number 6, is that a polygon? It's curved, so no. Should say, hey, it's curved. Let's go to number 7. Number 7, is it closed? Yeah, every side meets another side. Are there any curves? No. So is this a polygon? You betcha. Now this one's a little bit more difficult. We need to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12-sided shapes. Now again, there's 12 sides of this shape. So what we'd call that is we're going to cheat a little bit and just call it 12 gone. Again, if you Googled the 12-sided polygon, you'd come up with a name for it. It just might be a little long. Number 8, is this a polygon? Well, it is closed. Okay, but this guy is curved right here, so is it a polygon? Nope. Curved. Okay. So these two guys and this guy over here, when we had our tree that we just drew, these two guys would go over here as non-polygons. Okay. And then, we could probably split those up into more specific kinds, but we're not going to because that's not part of our class. All right. So let's go to the next one, quadrilateral interior angles theorem. Now, if we think back a little bit to last chapter, what we just tested over, if we had a triangle and we had 3 angles in here, what we knew about those 3 angles, that if I added those 3 angles together, we got 180 degrees. Okay, that's kind of what this is dealing with. But now, if we go up a notch and we look at something that is a quadrilateral, which is a more specific type, I didn't quite get a polygon there. Now imagine that these are all closed here. If we get a quadrilateral, and now we have four angles, W, X, Y, and Z. If a triangle is 180, what do you think a quadrilateral is? Well, let's jump up to our next magic geometry number. There are 360 degrees. So if I take those four angles, W plus X plus Y plus Z, those four angles are going to add up to 360 degrees. So what we're doing today is going to be very, very, very similar to what we've done in the past, except instead of 180, we'll have 360. Right? And then we'll jump into next chapter, chapter 8. We'll look at, hey, what happens if we go beyond 4? What happens if we go 5, 6, 7 sides? Well, it's actually pretty easy because you go 180, 360. Now, if you look at those two numbers, you may be able to jump to the next one, which is 540. And all I'm doing is every time I add a side, I'd add 180. Okay, but that's getting ahead of the game. Right. So let's go on this. Quadrilateral interior angles theorem states that if a shape is a quadrilateral, then the sum of the interior angles. Now remember, I'm talking about interior angles, all these guys on the inside. Remember, last chapter we actually dealt with some exterior angles. We'll deal with those in chapter 8, but we're not worried about those now. That's actually pretty easy, but we'll get to there in chapter 8. So if a shape is a quadrilateral, then the sum of the interior angles is 360 degrees. Okay, so that's a nice pretty conditional. If a shape is a quadrilateral, then the sum of the interior angles is 360. So we have our conjecture and our conclusion right there. Right? So if you need to, you can pause that and continue to write that, but I'm going to move on. So find the measure of the missing angles. Now, the first one I'm going to do the long way, just like I did when we started this with the triangle sum theorem. I'm going to put a little x here. Now, what I can do is I can start with that angle plus the 110. Again, I'm showing more work here than I have to. Plus 88 plus that 140. Now, when I add all three of those angles up, what is that going to equal? Well, if I add all four of those angles up, it's going to equal 360 degrees. Now, most of you know what we're going to do. We're going to take those three angles, we're going to add them up, and I get 338. This is your algebra. You're combining like terms on that left side. So x plus 338. Now, that's what that sum is. Those three add together is that. So 360. Now, most of you know that. All right, I'm going to go ahead and take this, and I'm going to subtract it over. Boom. So x is 360 minus 338, which is 22. Okay. So this missing angle up here is 22 degrees. Again, what you're saying, do we have to show all that work? No, you don't, because just like last class, all you have to do is you have to add all three of those up, take that number, and subtract it from 360. Okay, so let's go ahead and do that on number 10. We're going to take 110 plus 112 plus 95. We're going to add those three up. I got 317. And then we're going to subtract that from 360, and we should get 43. So this missing angle over here is 43 degrees. Okay. So do I need a whole heck of a lot of work on there? No, I don't, because you've kind of sort of already done this. Let's go to number 11. Now, this is something we messed up on. Some of us did on the test. Go ahead and write 90 in there if it helps you remember that, hey, there is 90 degrees here, 90 degrees here, and we're trying to find that guy. So again, we can write the equation. Now, I'm doing more than I have to here. And there's a reason, because you know, as always, I'm going to show you these little problems where you don't really have to do much work, and then we're going to get into some where we have those big, long, ugly expressions. Okay. All right, so we have that. So then what we need to do is take 90 plus 70, which is 250. So these three are 250. And then we're going to subtract that 250. And again, no, you do not have to show the work. I'm just doing it. You would know that you would just add those up, subtract it from 360, and you know the answer is 110. Well, if we look at that drawing, does that kind of look right? Well, yeah, it's obtuse, so it should be greater than 90. So the measure of angle C is 110 degrees. Okay. All right, so let's go ahead and do this real quick. We know we're going to take 360 minus, let's go ahead and add those up. 85 plus 75 plus your 80 is 240. So now we can subtract that 240. 360 minus 240 is 120. So that missing angle is 120 degrees. All right. Again, the reason I showed you this is for these problems. Now we're going to get a little bit harder. Okay. So now we're going to have some expressions in there. And I want to find the value of the variable and find the missing angles. Right? So if we look at number 13, we know it's quadrilateral, so we know we have 360 total. I can't start subtracting because I have these two variables here. So what I need to do is just start adding x plus 120 plus 60 equals 360. So we just go around the horn. We add up all those angles, x plus 120 plus 60. Let's go ahead. Now remember, we have like terms on the left side, so if you have terms on the same side, like terms on the same side of the equal sign, do what it tells you to do. What is 1x plus 1x? That's 2x. 120 plus 60 is 180 equals 360. So now we are in a two-step solve. We would subtract that 180 minus 180 minus 180. So that's Gandhi. So what we have left is we have 2x equals 360 minus 180, which is 180. And then we would divide by that 2 to finish our solve. Divide by 2, divide by 2. And x is 180 divided by 2, which is 90. So these angles here, since x is 90, these angles right here are going to be 90 degrees and 90 degrees. All right, let's go to number 14. Same process here again. Now, don't forget, these guys up here are 90 degrees as well. We need to go ahead and make sure we don't forget those guys. So let's write our equation. We're going to go right around the horn again. I'm going to start at x plus 10 plus, I'm going to 3x minus 30. And we got to add those two 90 guys in. Again, if you wanted to simplify that right away and go ahead and put 180, that is fine. All right. Again, we have to combine like terms. So on the left side, we have 1x plus 3x, which gives me 4x. We have 10 plus negative 30 plus 90 plus 90. 90 plus 90 is 180. That's 190. 190 minus 30 is 160. 360. And then we can go through our solve process now where we start solving for x. We need to subtract 160, subtract 160. Remember, the 60s are irrelevant right there, so we would go 4x equals 200. And then we can divide by 4. Now, what you need to remember right here was what's Mr. Dreher quick way of dividing by 4? Divide by 2 twice. That means take half of it. 200 divided by 2, or half of 200 is 100. And then take half of 100 is 50. So our answer is 50. But now remember, we need to go back up and find those angles. These two we know already. So what we need to do is take x, which is 50. 50 plus 10 is 60. And then we go 3 times 50, which is 150. 150 minus 30 is 120 degrees. Okay. So now we can double check ourselves. What do all four of these add up to? 180. Now what I want to do is I kind of want to review real quick. What do these two add to? 180. What do these two add to? 180. Now if you know what shape this shape is an a right trapezoid, meaning this side is parallel to this side. These two guys are those SSIA that we had back in the day. So kind of showing you what's going to be going on later on in the chapter. All right. Last one right here, so we're going to go to 15. Again, we have a quadrilateral, so we know that there are 360 degrees in here total. So we'd go x plus 2x plus 3x plus 4x. When I add all those angles up, I know that I will get 360 degrees. Now remember, we can't add side lengths together to get 360 degrees or 180 degrees. So now we add these like terms over here. That ends up being 10x equals 360, and this is a nice, short, sweet solve. We divide by 10. Divide by 10. That's Gandhi. X is 360 divided by 10, which is 36. Now remember, I'm going to ask you what are the angles. So if we go back up to the quadrilateral, this angle right here is 36 degrees. This is twice that, which is 72 degrees. This is 3 times that 36, which is 108 degrees. And this is 4 times that 36, which is 144 degrees. And if you want to take a wild guess what those 4 add up to, they add up to 360 degrees. Okay. All right. So that is lesson 6.1, dealing with quadrilaterals and the quadrilateral sum theorem and different types and classifying polygons. Your homework will be Math Excel 6.1. If you do have questions, please come and see me. Thank you and good luck.